Good morning all, my name is Udayrani and in this video let us know what ionization energy is and how it varies along the groups and periods of a periodic table. Ionization energy is the energy that is required to remove a valence electron from neutral gaseous, isolated neutral gaseous atom. Okay, so here I have drawn the structure of magnesium. In magnesium, the charge of nucleus is plus 12. And the valence electron is in the third orbit of the magnesium. To remove this electron, I have to apply some energy and that is called as ionization energy. Why we need to apply energy? Because there is an attraction between the nucleus and the electron. Nucleus is positively charged and electron is negatively charged, and there is an attraction between electron and the nucleus. That is called electrostatic force of attraction, and to overcome this we have to apply energy. Okay, that is ionization energy. This is the definition of ionization energy and it varies for every element. Ionization energy is different for hydrogen, lithium, sodium, potassium, and it varies for every element. And how it varies? There are 4 factors that affects the ionization energy of any atom. The factors are: 1. Atomic size. Atomic size is inversely proportional to ionization energy because see here, for magnesium, the valence electron is in the third orbit. So the distance between nucleus and the valence electron is more when compared to hydrogen. Here, atomic number of hydrogen is 1 and the valence electron is in the first orbit. So it is very nearer to the nucleus. So as the atomic size increases, the distance between the nucleus and the valence electron increases, so the strength of the attraction between these two decreases. So we can easily remove that electron. So atomic size is inversely proportional to ionization energy. Okay. Using that, we can say in periodic table, the first group, hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. As we are going down the group, the size increases because the valence shell is s orbital only, but as we go down the group, number of orbits go on increasing. Here the first orbit is there. For lithium, the valence electron is in the second orbit. For sodium, it is in the third orbit. For potassium, it is in the fourth orbit. As we go down the group, number of shells increases. So the distance between the nucleus and the valence electron go on increasing as we go down the group. So the strength of attraction between nucleus and valence electron is decreasing. So we can easily remove. That means ionization energy go on decreasing. So we can easily remove. So the amount of energy we have to supply for removing electron is higher for first hydrogen, and then it go on decreasing as we go down the group. Now see, for periods, here I have taken the second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Okay, so as we go from left to right, the atomic number increases but number of shells doesn't increase because the number of electrons in the valence shell increases but new shells doesn't add on. See here, for lithium atomic number is 3. So first 2 electrons in first orbital and third electron in the second orbital. 1s2, 2s1. For beryllium atomic number is 4. So the configuration is 1s2, 2s2. So the second electron is added in the second orbital. For boron also 1s2, 2s2, 2p1. So as we go along this from left to right, electrons keep on adding to the same shell, same orbit for the second orbit only. So here see, for lithium atomic number is 3, so the positive charge of nucleus is 3. For beryllium atomic number is 4, so the number of protons in its nucleus is 4, so the positive charge of the nucleus is 4. So as we go on like this, number of electrons keep on adding in the same shell, but the positive charge of the nucleus go on increasing. So the positive charge strength is increasing as we go like this. So the strength of the attraction between nucleus and electron go on increasing as we grow from left to right in a period. I hope you can understand. Here it is 3, 4, 5, 6, 7, 8, 9 and 10. So along a group, the electrons are adding in newer shells. I have mentioned the electronic configuration also here. 1s1, 2s1. So along a group, number of shells are adding, but along a period, in the same shell, number of electrons are go on increasing here. So the positive charge is increasing in a period. So the strength of the attraction between nucleus and electron is increasing along the period. So I already mentioned few factors affect the ionization energy. One is atomic size. Here, based on atomic size, it is increasing as we are going down the group. So we can say the ionization energy is decreasing, as though these two are inversely proportional. As atomic size and ionization energy are inversely proportional, we can say that ionization energy of elements is decreasing as we go down the group. But for periods, as we go from left to right, the nucleus charge is varying. The charge is increasing. So nuclear charge, effective nuclear charge is increasing as we go from left to right of a period. So the attraction strength is increasing. Ionization energy is also increasing. Okay. But there are few exceptions. Not many, few exceptions are there. See, ionization energy also depends upon the stable configuration. Some stable configurations offer more stability to the atom. So electrons from that stable configuration will stick to the atom stronger. So see here, what are stable configurations? Half-filled configurations. In case of nitrogen, we'll see that half-filled means for p orbital, half-filled means 3 electrons in the p orbital, and for d orbital, half-filled means 5 electrons. For f orbital, we generally don't use f orbital, but yeah, for f orbital, half-filled means 6 electrons. This kind of configuration is called half-filled. In this kind of configuration, the half-filled electrons are more stable. So we need to supply more energy to remove these electrons. So these are a bit different. Like they give more stability to the atom. So to remove that electrons from the valence shell, it is difficult for us. So ionization energy exceptionally increases in these kind of cases. One is half filled and the another one is fully filled. Fully filled means for p orbital 6 electrons, for d orbital 10 electrons, and for f it is 14. So see, in case of nitrogen, the configuration is 1s2, 2s2, 2p3. So the electronic configuration would look like this for 2p orbital, the valence shell 2p3. That means 3 electrons are there. So that is satisfying this half-fill configuration rule. So ionization energy increases here exceptionally. That means it is more than oxygen. These kind of configurations offer high stability to the atom. So to remove an electron from that atom, it is difficult for us. So the ionization energy is more. So here few exceptions happen. That means ionization energy of nitrogen is more than the oxygen. Why? Because of this half-filled configuration of nitrogen. Okay. And another case here, beryllium and boron. For beryllium, the configuration is 1s to 2s2. and for boron it is 2s2 2p1. Here that s orbital of second s orbital is completely filled, so it is offering more stability. So to remove this electron from this atom is difficult for us. That's why an exception happens here also. There is a jump. That is, the order goes like this. Lithium, actually by definition we feel that ionization energy must increase in this direction, but it doesn't happen here. Just a jump takes place. First boron comes and then beryllium. These two change like this. Same thing happens with nitrogen and oxygen also. Why this is happening? Because here the fully filled configuration is there for beryllium, and here for nitrogen the half filled configuration is there. The factors that affects the ionization energy of any atom, they are: one, atomic size. In groups, depending on this property only, we say that as atomic size increases, the ionization energy decreases. This trend is followed in every group. And in periods, as the nuclear charge increases from left to right, the ionization energy increases. Based on this, we say that. But few exceptions are there, that is beryllium, boron, and nitrogen and oxygen. They are half filled configuration of nitrogen and the fully filled configuration of beryllium. So based on this, we explain that. Another factor that affects is SPDF, the penetration effect. The ionization energy to remove an electron from s orbital is higher than P is higher than D, and D is higher than F. Okay. Thank you.